All right, today we're going to tackle a really important topic: hydrostatic testing for purified water systems. I know, it sounds super technical, but it is absolutely critical for safety and for regulatory compliance. And trust me, getting this wrong can have some pretty massive consequences. So let's dive in. So picture this. You've just invested millions of dollars in a beautiful, state-of-the-art, purified water system. Everything looks perfect. The welds are flawless, the design is immaculate. But there could be a silent killer lurking inside that system, one that could shut down your entire facility before you even start. And that killer is a failed hydro test. So the real question is, are you ready for that moment? Because this single test, well, it's often the fork in the road. It's the difference between a smooth, successful validation and months, literally months, of expensive delays and rework. The stakes really couldn't be any higher. To pass this test, first, we really need to get our heads around the fundamental rule that governs the whole thing. And this isn't just some random number somebody made up, it's a global standard. And it's all about engineering safety and meeting regulatory requirements. So, what exactly is a hydrostatic test? Well, in the simplest terms, it's basically a stress test for your pipework. We fill the system up with water, and then we pressurize it way beyond what it would normally handle. Why? To prove that it's structurally sound and, of course, that it's completely free of leaks. But look, this isn't just about finding a few drips. There's a huge regulatory angle here. You got bodies like the FDA, and they're guided by ASME standards. They require this test as absolute proof. It is a non-negotiable step to verify that your system is, and this is the key phrase, fit for purpose. And that brings us to the single most important number in this whole process: 1.5. According to the ASME B31.3 standard, which covers process piping, the test pressure has to be exactly 1.5 times the system's maximum design pressure. That right there, that's the benchmark, that's the target you have to hit. Okay, enough of the theory, let's get into the practical side of things. To make sure you pass, you need a really methodical approach. So let's walk through the 5-step roadmap for a successful hydro test. We're going to break down each of these stages. First, preparation and isolation, then the fill, venting, pressurization, and finally, the hold. Getting every single one of these steps right is absolutely essential if you want an accurate and successful test. So, in step 1, it's all about protection. You have to isolate the section you're testing, but even more importantly, you have to remove any sensitive instruments. Think about things like your diaphragm gauges or your UV lamps. They were not designed to handle 1.5 times the normal pressure. You'll destroy them. So you replace them with what are called dummy spools, which are basically just temporary sections of pipe. This one move can save you a fortune. Now for step 2, the fill. And listen, this is a huge pro tip. Never, ever use raw water or utility water. I'm serious. If you fill your high-purity, very expensive 316L stainless steel piping with low-quality water, you can get instant surface corrosion. It's a process called rouging. And even worse, you're basically rolling out the welcome mat for biofilm before you've even started. You have to use ambient purified water. End of story. During step 3, venting, this quote just says it all perfectly. You have to open up all the high-point vents and let every single last pocket of air escape. Why? Because trapped air is compressible. It acts like a spring, and that can lead to dangerously unstable pressure readings. Water, on the other hand, isn't compressible. It's like a rock. For a safe, accurate test, we definitely want the rock. So after you gradually pressurize the system, we get to the final step, the hold. You need to maintain that 1.5x pressure for at least 30 to 60 minutes. The industry gold standard, what you're really aiming for is 0 drop on a calibrated pressure logger. If there's any drop at all, it's time to investigate. But what happens if the pressure does drop? It's not always a total catastrophe. Understanding how to troubleshoot is absolutely key. So let's look at the most common reason for what looks like a failure. So you're watching the gauge, and you see that needle just slowly start to fall. Your heart sinks. But the very first question you have to ask is this: is it a genuine leak in my system, or is something else going on here? This breaks it down perfectly. A true leak causes a steady, continuous pressure drop, and you can usually find visible evidence, like water weeping from a weld or a gasket. But a thermal shift, now that's sneaky. If the temperature in the room drops, the water inside the pipes cools down and contracts, and that makes the pressure fall. It's a false negative. There's no leak at all. Okay, So you've done it. You've completed the test, you've figured out any issues, and you've achieved a stable hold. Now comes the final step. You've got to prove it. It's time to assemble all the right documentation to pass your official site audit. Your evidence here is everything. Your final report needs to have 3 key things. First, proof of zero leakage from your pressure logger. Second, a valid NIST traceable calibration certificate for that pressure gauge. And third, a report confirming that the water you used met all the right purified water specs. You need all 3 of those. You know, when it comes right down to it, mastering the hydro test isn't just some technical exercise. It is the backbone of your system's mechanical integrity. Getting it right proves your investment is sound, and it saves you from some truly devastating delays. So I'll just leave you with this one thought. Is your system's integrity truly verified, or is it just being assumed? This explainer drew on key insights and materials from the Indian Pharmacist. Thanks for watching.